at MIT, people don't just start one thing. They come to the school with the vision that they want to be part of changing the world, not once, but basically in everything that they do, they try to change the world. So in December, we had a conference on serial entrepreneurship, and the interesting thing that comes out of that kind of discussion is it turns out that everybody who shows up at that event has that ambition. I'm going to introduce a speaker now, Adam Paxson, who was part actually of founding LiquiGlide, which we have already heard about. And then, not happy with that achievement, he goes straight for the next startup, and not happy with founding it out of one lab, he joins forces with another MIT lab. This is a startup that comes out of two MIT labs, the Varanasi lab previously mentioned, and Karen Gleason's lab, who's now a provost at MIT. Without further ado, I'm going to give him the floor, but just to say that the key word here to continue and to make this session flow is actually also about liquids. Thank you.
Thank you, Trond. So I want to talk about how people at MIT love to solve big problems. I think I took 3091 from Professor Sadoway back in 2005, and as a very naive student, wanted to solve global warming. And the thing is, at MIT, you can actually chip away at a problem that big, and that's what we're trying to do at Dropwise. We're bringing a new coding technology, both materials and a new manufacturing method, to try to clean up how big industry operates. So last year was a really big sea change in global warming. I think we finally got international consensus that we've got to do something about it. The question is now, what do we do about it? So the last issue of MIT's Tech Review had a certain dramatic take on what we do about it. But let's actually be good engineers here. Let's do some quick root cause analysis to see what we can do about something as big as climate change. So what's contributing to all of these emissions? We'll pull data from a couple years ago for the contributors to emissions, and the usual suspects come up. Everyone knows that power plants account for more than a quarter of the world's emissions, and they're followed really closely by manufacturing. You'll see they're almost 20%. So this includes everything like refineries and chemical processing plants, really big factories putting out really big quantities of emissions and fuel consumption. But the part that a lot of the public doesn't realize is how big water consumers those are. If you pull up the water consumption data, power plants and manufacturing together are second only to agriculture in the consumption of water. So I think we can all agree that if you want to solve the problem, a really good place to hit is going to be power plants in manufacturing. Okay, so next step, what do we do about these processes? Well, you look into a typical industrial process, whether it's a power plant or a chemical refinery, and you see that the entire thing is driven by heat transfer. It's really simple. You just take a cold fluid and heat it up by flowing a hot fluid by it and cooling that down. And you separate the two with a really thin wall of metal, thinner than a credit card. And you call this thing a heat exchanger. You probably know the more common versions of this. You have boilers in your houses, you have radiators in your car, so heat exchangers are everywhere. Most of the world's energy at some point passes at least once through one heat exchanger. Most of it passes through multiple heat exchangers. So here we have the next step. Let's target heat exchangers. If we can improve heat transfer, we can make a really big dent in global emissions. And luckily, there's a lot of room for improvement here. Heat exchangers get filthy. They get super dirty. So we've been talking with customers. Here's a picture of an ethylene condenser. And remember, you have this really thin wall of metal that's supposed to be transferring heat through that wall. So even the tiniest bit of crud starts to have an effect on the performance of these things. And you get cases like this. We're talking with customers whose processes are supposed to be pumping out hundreds of tons per hour of a chemical that they sell for $450 a ton. And this heat exchanger is getting scaled up so bad, it's being clogged, just like an artery gets clogged with plaque, so badly that they have to shut down their entire plant for a whole day every 5 days. It's unbelievable. So the question we ask is, why do they put up with this? Why is this still a problem? We've been working with heat exchangers for centuries. How could this still be an issue? And the problem is that all the technologies out there for dealing with fouling and corrosion, the things that ruin these heat exchangers, you usually put a coating on, say, a pipeline where you don't really care how thick the coating is. But remember now, we're dealing with heat exchangers. You have that thin metal wall again. If you put a thick coating on that wall, you ruin the heat transfer just as bad as any fouling or corrosion will. So any liquid method where you have to rely on just dumping a ton of material and then evaporating the solvent out to try to leave your coating behind, that's just not going to work. The other reason that it won't work is, as with many materials challenges, manufacturing. The scale of these things is huge. This is an illustration of a typical steam condenser you'd see on the back end of a power plant. This is taking the steam from the turbine, condensing it down into a liquid, pulling steam through the turbine. There's a little guy for scale. So these things are just unbelievably huge. So they're built around these tubing bundles. You can see on the right side here, you have these tubes packed so tightly, you can't possibly fit a spray nozzle to spray these tubes. And the thing's so big, you can't flood it up and fill it with a liquid. You need to show up with an Olympic swimming pool of coating material. So that's just not economical. So what we did was take a completely different approach. We thought, what do we need to do here? We need a completely different process of putting materials across big, large surfaces. So we took a process that has its roots more in semiconductor fab that doesn't rely on any liquids. So we take our coating materials and we flow them into the heat exchanger in the vapor phase. And so what this lets us do, we can now grow essentially molecule by molecule right up to the thickness that we're after, where it's thick enough to be durable, but thin enough that it doesn't have any negative effects on the heat transfer. And this completely changes the economics of coating things like big industrial heat exchangers. Your run-of-the-mill anti-fouling coating, you need about a pound of material per square yard. Our coatings use less than a pound per acre. So we are many orders of magnitude lower on that scale. So it just completely changes things. So we're really excited about this. This is here an example of one of our coatings at work. So this is condensing steam at 100 Celsius. So a lot of coatings, manufacturers like to put them through a test called the 85-85, where they expose it to 85% humidity at 100 degrees. Well, this is our 100-100 test. This is 100% humidity, 100 degrees C. We've run this until our testing rig breaks. So the thing about our coatings is that we can graft these polymers. We can form a really strong covalent bond between the polymer and just about any metal. So we can do titanium, steel, aluminum, copper, anything you use for a heat exchanger, we can graft these coatings to. And so this has a really big effect on a power plant. Let me see if I can play this again. On the left here, this is an uncoated piece of essentially a metal that when it condenses the steam wets the metal and it forms this thick blanket of liquid. That blanket is almost a millimeter thick. That just kills your heat transfer. So on the right, what we've done is we put one of our water repellent coatings that breaks up that blanket of liquid. The heat transfer on the condensing side goes up by a factor of 7. And so for the power plant overall, the efficiency improves by almost an entire %, which that's a big scale. So to put that in perspective, GE spent more than $1 billion investing in the research program for its last steam turbine, trying to squeeze just a couple % out of their steam turbine. So a % is a big deal for a power plant. So I'm very lucky to be working with an incredible team. Again, this is coming out of a collaboration between 2 labs at MIT, Kripa Varanasi in mechanical engineering and Karen Gleason in chemical engineering. So Kripa's coming with almost half a decade of experience at GE Global Research with heat exchangers and large industrial processes. Karen has been refining this manufacturing method for almost the past 2 decades. And I'm working with experts in both the technology and the business side. So I've been fortunate enough to be able to snap up all the experts in the world of this coating method. And so far in the last year, we've gotten a number of awards and grants that the technology has won, and been featured in the media for even something as unsexy as dirty heat exchangers. We're pretty happy about that. And so we've gotten a lot of commercial interest from this. A lot of these actually ILP leads, one of which has led to a strategic partnership that we've formed with Henkel Corporation to bring this technology into some applications of mutual interest. So we're very excited about where we're going. We're very, we owe a lot to the IOP for fostering these relationships that we've started to form with these, what are eventually going to be very large customers for us to deal with. So that's been very helpful from a startup's perspective to have the help of the IOP there. So with that, I'll let us all get off to lunch quickly, but I'll look forward to speaking to anyone who wants to later. Thank you.